Students, now let us write one more note. V is equal to lambda into F. This equation is for unbounded medium. Unbounded medium means a uniform plane wave actually. When there is no waveguide, that is the meaning. Lambda is called unbounded wavelength. So, here lambda is unbounded wavelength. Unbounded medium means uniform plane wave. Uniform plane wave. Next, in place of velocity, you put guide phase velocity, then it should be guide wavelength. So, for example, I told you whenever EM wave is outside the waveguide like this, so here EM wave is coming like this here. This is uniform plane wave. There is no waveguide here. Here it is coming EM wave. This EM wave frequency is F. Velocity is 1 by root mu epsilon. Then lambda is wavelength of wave traveling here. This is outside waveguide. When EM wave enters into the waveguide, I will draw the diagram that also. When EM wave enters into the waveguide, then frequency doesn't change, but velocity changes. The way velocity changes, similar way wavelength also changes. For example, Vg is equal to V by root of 1 minus Fc by F whole square. Lambda g is equal to lambda divided by root of 1 minus Fc by F whole square. So, जैसा वेलोसिटी चेंज होता है इक्वेशन, उसी तरीका में वेवगाइड का लेंथ भी चेंज होता है, राइट. नाउ one more equation I will write here. This is valid for wave guide. For wave guide. So here Vg means guide. Guide means waveguide. Guide phase velocity. Lambda g means guide wave length. So Vg means guide phase velocity, lambda g means guide wavelength. Okay. Next, third one is V is equal to lambda into F. Once again I wrote this one. If I put C here, then I have to put C here, but this is V. Lambda c means cutoff wavelength and Fc means cutoff frequency. You will ask me the question that this equation is valid when wave is traveling in unbounded medium. This equation is valid when wave is traveling in a waveguide. Where this equation is valid? Answer: there is no propagation. Whenever F is equal to Fc, there is no wave propagation. Then what is this equation? That is this equation gives conditions. For example, if F is equal to Fc, there is no wave propagation. That Fc, this Fc value is decided by the waveguide parameters I told you, mu epsilon a, b, because Fc is equal to V by 2 root of m by a whole square plus n by b whole square. So this Fc value is decided by epsilon mu. That means parameters of the medium inside the waveguide, and a value, b value. So Fc is the property of the waveguide. Similarly, lambda c is equal to 2a. You have seen just now lambda c for dominant mode. That is 2a is what? That is decided by the waveguide. So this is the equation, nowhere valid, but this represents waveguide dimensions. So if you want relation between Fc and lambda c, then this equation is used. So that means this equation is used near cutoff, not near, at the cutoff. So this equation is valid for cutoff. So this equation is valid for cutoff. So if you put cutoff wavelength, then you have to take here cutoff frequency. This equation gives relation between cutoff wavelength and cutoff frequency. For cutoff, that means this equation gives relation between cutoff frequency Fc and cutoff wavelength lambda c. Okay, right. Now after discussing this one, I will give some equations for lambda g. Okay, I will write here observation. Observation means just you have to observe, no need to study that in detail. But in that observation, while listening the class, you listen carefully, and wherever box comes, you have to learn that one. थोड़ा सा ध्यान से सुनते रहो आप लोग. Okay, I will show here in the waveguide. Dear students, this is waveguide. We have taken this as a x-axis, this as a y-axis, this as a z-axis. ऐसा मत पूछ लो सर ये x है ये y है, ऐसा मत पूछ लो. हम लोग ऐसा लिया था. This is x-axis, this is y-axis, this is z-axis. What is the meaning of waveguide axis? The center line, this one. The center line of the waveguide is called waveguide axis. The center line. Okay? The center line of the waveguide is called as waveguide axis. For example, if any EM wave travels along the axis of the waveguide from input end to output end, then that EM wave enters like this, straight away it goes. That means it doesn't experience the waveguide behavior. What is waveguide behavior? If EM wave hits this boundary, then it is reflected back. But there is no waveguide here. If EM wave is traveling, it can go. Nobody stops that. Similarly, here also, if EM wave enters the waveguide along the waveguide axis, then it behaves like unbounded wave propagation in unbounded medium. Then it is not reflected by conductor walls because this is not touching the conductor walls at all. So in the waveguide, if any EM wave travels along the waveguide axis, then you can call that as a wave traveling in unbounded medium. You can think that there is no waveguide at all if wave travels along the waveguide axis. Now I am drawing the diagram here. So actually what we do, I will show only top view, student. For example, I will show you top view. So top view is like this. Like this. Here, little. Okay. This is, you can say this is top view, or otherwise if EM wave hits like this, you see from top. Anyway, doesn't matter. Top view or side view, you can take here also. Side view means this one. Right? Or otherwise, if EM wave is hitting this boundary like this and like this, that means it is hitting the top boundary like this and like this, then you will be taking a side view. Actually, you can take side view, no problem. If EM wave hits this boundary like this boundary, you can see the side view. If EM wave hits this boundary, then it will be going like this, and it will be going like this and then like this. So you can see top view. Any view you see, doesn't matter. Because students, what I am telling now, some EM waves enter along the waveguide axis. Some EM waves enter like this, then they hit the side boundary and they go like this. Some EM waves hit this top boundary, then they go like this. Doesn't matter. Now I was telling you what is this. This one is called wave guide axis, that is central line. So I told you if any EM wave travels in the direction of waveguide axis, that is like a uniform plane wave, this equation is valid. And you need not to take as if wave is traveling in the waveguide. No need to take. Okay. Now, if EM wave travels like this, then it hits this conductor wall. Again, it will go like this. It hits like this. It goes like this, and again it hits. It goes like this. Ultimately, any EM wave entering like this. This is EM wave here. It hits, again it comes back like this, and ultimately it will go out of this. It will go out. That means waveguide is over, it will go out. Here input is given, there output is coming. For example, here we can connect radio mirchi signal or otherwise satellite signal. Then it is that signal is generated here, and we are sending through the through the waveguide. Once you send here, what we do here, we put the horn antenna, HORN, horn antenna. Horn antenna means it is like this. It is like this here, and here also it is like this. Here also it is like this. Here also it is like this. They are called microwave antennas. They are not there in the syllabus. Earlier microwave engineering was there. Microwave antennas were there. Now it is removed from the syllabus. I was teaching that microwave engineering, so that is removed. That is good for the students, because for students that is very difficult subject. Anyway, why to open like this, students? That is called horn antenna. In the waveguide, you have seen impedance is equal to eta g, depends on cutoff frequency. We have seen eta g is equal to eta by root of 1 minus fc by f whole square. Then here, if you are doing like this, means a comma b dimensions are changing, then impedance changes. That means the waveguide has some impedance. This medium has 120 pi impedance. If you do like this, then a comma b dimensions change, then impedance also changes. Then waveguide impedance is gradually changed in such a way you get 120 pi, then impedance matching is done. Then the whatever signal is going in the waveguide, that is radiated into the air through this horn antenna. That is one of the example I told you. So this is called output side. You will be sending the signal to the medium, into the air or somewhere else, wherever you want. Okay. Now, dear students, once again, waveguide means not wood. It is a perfect conductor. Okay. Every time I have to make you recall. This EM wave here, this is EM wave. This EM wave makes some angle called theta. This theta is angle between EM wave and waveguide axis. That is called wave angle. That means wave angle means the angle between EM wave and waveguide axis. That is called wave angle. Okay. Now, when any EM wave travels in the direction of waveguide axis, that behaves like a uniform plane wave. That means because it is not hitting the conductor, then no need to bother about a comma b dimensions. So then in this direction, for example, if I take a vertical line here, in this direction, whatever wavelength is there, that is called lambda. In the direction of wave propagation, this one, in the direction of wave propagation, whatever wavelength is there, it is called as lambda g. in the direction of wave propagation, whatever wavelength is there, it is called lambda g. In this direction, whatever velocity is there, that is called v. In this direction, whatever velocity is there, that is called vg, guide wavelength. Guide velocity, not guide wavelength. Lambda g means guide wavelength. In this direction, velocity vg is there. This velocity, that is called guide phase velocity. This one. Now, I wanted to tell you one thing, then I will go ahead. What I want to tell you, some students may ask that, sir, why don't we send signal along the axis of the waveguide, so that we are not bothered about this discussion? No, it is not in your hands. ये आपका हाथ में नहीं है, सुनता नहीं है वो आपको EM wave. Actually, practically speaking, this is in centimeter, this is in centimeter. EM waves, no, they have lot of dispersion, so that they will hit the surface at all the EM waves, no, they will hitting at angles only. You don't expect EM wave travel along a straight line. It is not a human being. You can't instruct that you go straight, you go straight. You can't instruct that. ओके जैसे आदमी लोगों को बताता है सीधे जाओ, ऐसे थोड़ी बोल सकता है EM वेव को, नहीं चलेगा ऐसा. So always, for example, in fiber optics also, that light wave will be hitting the fiber at some angle, like this, multiple reflections only. Anyway, now let us get the relation between lambda g and lambda. It is Pythagoras theorem. 90 degrees is there here, 90 degrees. Now, what is cos theta? Can you tell me here? Cos theta is equal to, definition of cos theta is adjacent divided by hypotenuse. That means cos theta is equal to, adjacent is lambda and hypotenuse is lambda g. From this, lambda g is equal to lambda by cos theta. Okay, so this is equation number 1. Already we have one equation, dear students. What is that equation? Lambda g is equal to lambda by root of 1 minus fc by f whole square. Already I derived this equation, student. Yes or no? Now, in this, f is proportional to 1 by lambda and fc is proportional to 1 by lambda c here in this equation. So, lambda g is equal to lambda divided by, what do you say, 1 minus of lambda by lambda c whole square. This is equation number, say, 2. Now, this is the guide wavelength in terms of lambda and lambda c, and this is the guide wavelength in terms of lambda and wave angle. I will write later on what is theta. So, compare equation 1 and 2. Compare equation 1, 2. Then here numerator lambda, here lambda, denominator cos theta, this one same. So, cos theta is equal to root of 1 minus lambda by lambda c whole square. Now, cos theta is written as 1 minus sin square theta root, so lambda c whole square. You compare both sides. After comparing sin theta, you get lambda by lambda c. Okay. Once again, that lambda by lambda c is nothing but fc by f, like this only. I wrote in terms of lambdas. You can write in terms of fc's also. This one will come here, and that means fc by f. Now, sin theta for Mn mode is equal to, you have to take cutoff frequency for Mn mode divided by f. So, this is the formula, dear students. So, here theta Mn means wave angle for Mn mode. Theta Mn means a wave angle for Mn mode. Okay. wave angle is the angle between EM wave and waveguide axis. Waveguide axis, that is the meaning of wave angle. Okay. This is one formula. FCMN already you know, no need to write. Cutoff frequency for MN mode. F is operating frequency and F is operating frequency. That means how much frequency you are sending. Then FCMN is cutoff frequency for MN mode. Okay. Right, dear friends. Next discussion in the observation. Lambda g is equal to lambda by root of 1 minus fc by f whole square. And already we have written lambda g is equal to lambda by root of 1 minus lambda by lambda c whole square. Now lambda g is equal to lambda divided by, from this you do one thing, I will write like this, 1 by this lambda 1 by lambda root of 1 minus lambda by lambda c square. Ultimately lambda g is equal to 1 divided by, you send 1 by lambda inside then it becomes 1 by lambda square. Here 1 by lambda square cancel. So ultimately it becomes you send inside 1 by lambda square minus 1 by lambda square into lambda square divided by lambda c square. So ultimately this cancel. Okay. Now you take reciprocal both sides, reciprocal 1 by lambda g, then it becomes root of 1 by lambda square gone, lambda c square, and 1 by lambda g square is equal to take whole square, 1 by lambda square minus 1 by lambda c square. So 1 by lambda square is equal to, you send this side, 1 by lambda g square plus 1 by lambda c square, like this. So this is the relation between lambda, lambda g, lambda c. There are three lambdas. Lambda is wave length in unbounded medium. Already I wrote them. Next, lambda c is cutoff wave length. For example, for TE10 mode, lambda c is equal to 2a. That is decided by the waveguide dimensions. Lambda g is the guide wavelength. What is the meaning of guide wavelength? When EM wave is traveling inside the waveguide, then how much wavelength it has? That is called guide wavelength. Guide wavelength means when EM wave is traveling inside the waveguide, how much wavelength that EM wave has? That is called guide wavelength. So these three things. Okay. No. Okay. You remember this equation. So this is the equation which gives relation between lambdas. How you remember this? Suffix is there lambda g and here c and no suffix, and suffix terms one side, without suffix one side. It is nicely formed here. So dear friends, now let us write note on the velocities. Guide, that means waveguide, phase velocity, otherwise guide constant phase velocity, both are same. Guide phase velocity v small g symbol Actually, I am writing V like this, student. V, velocity symbol. V small g is defined as V small g is equal to omega by beta for what do you say, unbounded medium. Beta g for waveguide. Okay. And after doing mathematics, we got that this you see here, you see backwards, I did mathematics, you got V divided by root of 1 minus Fc Mn divided by F whole square, and this gives the guide phase velocity for Mn mode you have seen after doing the mathematics. So where V is equal to 1 by root mu epsilon, and V is velocity or otherwise phase velocity in an unbounded medium. Okay. Now second one, group velocity symbol V capital G. I told you different books use different symbols. Don't confuse. I told you what is important is velocity divided by this factor, and symbol might be any symbol, that is called guide phase velocity, and velocity multiplied with this factor, and symbol may be any symbol, that is called group velocity. I told you already, once again I am telling. So group velocity V capital G is the velocity of group of frequencies or velocity of message signal. Velocity of message signal. Velocity of message signal carried by EM wave. Carried by EM wave. It is defined as V capital G is equal to d omega divided by d beta g. This is the definition. And after doing mathematics, you get V root of 1 minus Fcmn by F whole square. This gives what do you say, group velocity for Mn mode. Okay. So V capital G Mn is group velocity for Mn mode. Once again, here V is same thing only. So V is 1 by root mu epsilon, right? And if you want, I will do here arrow mark I am putting, I will do the mathematics. So already you know beta g, you have remember omega root mu epsilon root of 1 minus Fc by F. Fc by F can be written as so this one whole square. So that is beta g is equal to, you send this inside, and if you send that omega square mu epsilon minus omega c square mu epsilon under root. Actually from this after taking common factor you got this one, but you are habituated to remember this, that is why I am writing this, and again I am getting this one. आपको ये आदत बन गया होगा, ये याद रखना, इसलिए उसको लेके मैंने ये किया. सच में इससे हमको ये आया था, कोई बात नहीं है. So you differentiate this with respect to omega. It is like root x formula 1 by 2 root x. Then again inside term you have to differentiate. So d beta g divided by d omega is equal to 1 by 2 root omega square mu epsilon minus omega c square mu epsilon, and you differentiate this, then you get 2 omega, right? Now 2 to cancel, that is equal to omega divided by, you pull out this once again, omega square omega square mu epsilon you pull out once again, you get 1 minus omega c square mu epsilon divided by omega square mu epsilon. Okay. Now d beta g divided by d omega is equal to omega here na, you pull out now omega root mu epsilon comes. Okay, yeah, you pull out, you get. So this one, this cancel. Okay, then here 1 by 2 root x, that is fine. You pulled out this. Okay, omega here d omega by d beta. Anything print miss? So d beta g divided by d omega, this becomes v na, v by this one. Then how come it is 1 by v is coming? Okay. So here root x, 1 by 2 root x. Here na students, actually something is missing here na. You differentiate this one, you get 1 by 2 root x. You differentiate this one, omega d by d omega, omega square is 2 omega, mu epsilon is also there na here. So mu epsilon is also there here. That is missing here, right? Now omega square mu epsilon you common inside root. If it comes out, then omega root mu epsilon, it becomes omega gone. So root mu epsilon divided by, after cancellation, root of 1 minus this cancel, and 2 pi f c by 2 pi f whole square. So once again f c by f whole square. Now the definition of group velocity is d omega by d beta g, that is nothing but group velocity is equal to reciprocal of this one, that is 1 by root mu epsilon, root of reciprocal of this one, students. So that means from this you got Vg is equal to, this is V and root of 1 minus Fc by F whole square. That's what written here. It is just observation or otherwise hint for you, and no need to study this hint. ये सीखने की जरूरत नहीं है 100%. कोई पूछता नहीं है इसको, right students? Now actually what is the meaning of this Vg? If you want, I will tell you. For example, this is waveguide and this is waveguide axis, and already I have shown you this diagram. What is this? This is EM wave is traveling like this, right? And in this direction velocity is called Vg, small g. That is guide phase velocity. Now whenever EM wave travels for this much distance, you can see, but EM wave traveled from here to here means in the waveguide axis direction, because ultimately EM wave may go like this, but ultimately final outcome is to be in the direction of waveguide axis. So in the direction of waveguide axis, what is the velocity of the message signal? Message signal, you know, in communication systems you study, message has group of frequencies. So that is why message signal velocity is nothing but a group of frequencies velocity. So in the direction of waveguide axis, how much velocity is there for the EM wave? So you can see here, it traveled longer distance here. That is why Vg is more than V. Vg is more than V. I will write after some time that also. But in the direction of waveguide axis, it traveled less distance. That is why group velocity is. Actually, students, what I am telling is, EM wave traveled from here to here, cross path is taken. That is why more distance is there. But even then, wave is here only. That means on the wave, message is there. But message signal traveled only for this much distance in the direction of waveguide. It traveled less distance. It traveled less distance. That means less distance means less velocity. So this is in this direction. If you split this component in this direction, then whatever velocity is there, that is called group velocity. So velocity of the message signal in the direction of waveguide is called group velocity. That is always less than the velocity. That's why here less velocity. I told you, dear students, for the wave propagation, f should be greater than fc, then this factor is less than 1. This factor in denominator, vg, is greater than v. So guide phase velocity is more than the velocity because it is taking zigzag path, so it is traveling longer distance, so that's why velocity is more. And coming to this velocity, this factor is beside v, that means it is numerator. For wave propagation, this factor is less than 1, and that means v capital G, group velocity, is always less than v. Right? Now that note also I will write here. First point over, second point over, third point. Third point. V guide phase velocity, I will write like this, student. Okay, you write already how you might have written this, so let us not strike up that with this one, comma, V group velocity is less than V for dielectric field, waveguide, for dielectric field waveguide, because for wave propagation, f should be greater than fc, and root of 1 minus fc by f square, this factor is always less than 1. This is the point you have to remember for entire chapter. Pura chapter ke liye yaad rakhna. For wave propagation, f greater than fc, and this factor is always less than 1. Right? Next, fourth point. Vg greater than c and v capital G less than c for air-filled rectangular waveguide. So here air-filled means this v is equal to 1 by root mu epsilon. For air-filled waveguide, that v becomes c. So in this direction, velocity should be more because wave is traveling for longer distance. But message is here only. Message is here means wave traveled from here to here means in the direction of waveguide axis, message traveled from here to here. That means this is less distance, less velocity, that is group velocity. So group velocity is actual velocity, that is less than the light velocity. This is actual velocity, practically. Now, third point over. These are all objective questions, student. These are all objective questions. So some students say like this: group velocity is greater than light velocity, and this phase velocity is guide phase velocity is greater than light velocity, and group velocity is less than light velocity. They say that is wrong statement. Every time they say that only. Be careful. If it is dielectric waveguide, this is the case. Students don't give importance whether it is dielectric field waveguide, whether it is air field waveguide. For every case, they say the story only. Group velocity is greater than light velocity, guide phase velocity is greater than light velocity, group velocity is less than light velocity. Don't say every time that statement. Mentioned here, if it is air field, then only you have to say that one. For dielectric field, it is V. V means C by root mu or epsilon r. So, be careful while giving the statements, because in examination that small difference gives negative marking. Okay. Now third point, fourth point. Next, fifth point. Here, anyway, okay, I have written covered all the things regarding velocities. Students, this fifth point, if you want, you can write this one. Guide phase velocity multiplied with group velocity, that is equal to guide phase velocity is V divided by root of 1 minus Fc by F whole square. Then Vg is V into root of 1 minus Fc by F whole square, right? Now this cancel. So guide phase velocity multiplied with group velocity is equal to V square. Okay, then where V is 1 by root mu epsilon, that is C by root mu r epsilon r, that is a unbounded phase velocity. This is for dielectric, this is for dielectric field waveguide. Similarly, guide phase velocity multiplied with group velocity is equal to C square. Simply, this becomes mu r is equal to epsilon is equal to 1 for air field. This is C square for air field wave guide. Dear students, why I am carefully writing one separate point for dielectric field, one separate point for air field, the separate point for dielectric and separate point for air field, because every time don't say Vg into V small g into V capital G is equal to C square. That is valid only for air field, students. Okay, this is all about velocity points which come in examination, right? So students, now I am writing one observation. Observation means you need not to learn these formulas, but they are general formulas. So average power carried by the waveguide, and I will write the formulas. And after that, always we send the energy through T10 mode. The reason is, if we send the energy through different modes, different modes have different delays. So that is why it is difficult to collect the energy at the output side. So if we always send energy through single mode, then it is easy to collect the energy at output side. That is why always we send the energy using the dominant mode. So for dominant mode, power carried by the waveguide formula is important. I will do the derivation also. Now before that, let us write formulas for average power carried by the rectangular waveguide. So observation, I am writing general formulas. Observation, first one, power, that means average power, students, that is average power. Always average power only we will talk of. Average power carried by rectangular waveguide in TEMN mode. In TEMN mode is PAVG is equal to 1 by 2 eta g for TE-Mn mode, double integral electric field square, that is electric field x component is there, electric field y component is there, then waveguide open ends have x variable and y variable, so that x varying from 0 to a and y varying from 0 to b. Actually student, it is like this. Average pointing vector is I am writing like this. Average pointing vector in the uniform plane wave. Uniform plane wave is half EI0 square divided by eta into power flow direction. For example, half EI0 square divided by eta, power flow direction is AZ. Then average power is equal to double integral PAVG bar dot ds bar. So double integral half into EA0 square divided by eta AZ dot then ds bar in z direction is dx dy AZ, dear students. Now this is for uniform plane wave, already you have studied this one. Now for rectangular waveguide, AZ dot AZ is 1 a unit vector. For rectangular waveguide, dx dy came, and x varying from 0 to a and y varying from 0 to b, that is 1 point over. Next 1 by 2 came outside, and eta g denominator that came outside, and because it is not a function of distance, and in the rectangular waveguide for TE-Mn mode, impedance is eta g TE-Mn. Okay, eta g TE-Mn. Now, for wave traveling in z direction, total electric field can have x component and y component. If electric field x component is there, then electric field x component and magnetic field y component carry the power in z direction. If electric field y component is there, electric field y component and magnetic field z component, x component carry the power in z direction. So both carry the power if both are there. If only one component is there, one component carry the power. So this is a in the rectangular waveguide, total electric field is EX-AX plus EY AY, and modulus of electric field, in place of this you get modulus of electric field whole square. So modulus of electric field is root of EX square plus EY square. Then here modulus of E whole square is there. So modulus of E whole square means EX square plus EY square you get. So this formula is similar to this one only, but it is rectangular waveguide. So anyway, I am telling you, no need to remember these formulas because always we send power using TE10 mode. For that I will do derivation also. You remember that formula, that is more than enough. Anyway, for the sake of continuity, I am writing them. Now, one more thing. Here, this formula I am writing here. This is nothing but double integral half in terms of hi0 I will write na. This becomes hi0 eta, denominator eta, here beside this eta az dx dy az. So az dot az is 1 actually. Now dx dy, if magnetic field is there na, take magnetic field whole square, then impedance is beside that, it is in numerator, here it is in denominator. That is for TM mode actually. This is for TE mode, but if magnetic field is there, eta is in the numerator. If it is TE mode, you take eta g TE here eta g TE, and you take eta g TE. For TM mode, same equations, but here impedance for TM mode you have to write. Here also impedance for TM mode. Once again I am telling students, if electric field comes na, electric field square by this impedance is in denominator. If you write in terms of magnetic field square, impedance is in numerator. For TE mode, in place of eta, you put eta g for TE mode. Here also eta g for TE mode. For TM mode, you put here eta g guide impedance for TM mode. Here also eta g guide impedance for TM mode you have to put. So I am linking these formulas with the uniform plane wave. That is nothing but 1 by 2, or otherwise 1 by 2, that is correct only, eta g Te Mn impedance comes in the numerator if I use magnetic fields here. So double integral magnetic field x component square, magnetic field y component square, then dx dy, x varying from 0 to a, y varying from 0 to b, where eta g Temn is equal to eta by root of 1 minus fcmn divided by f whole square, and eta is nothing but here root mu by epsilon, this one, where eta is root mu by epsilon. Okay, right. Now second one, average power carried by a rectangular waveguide in TMMN mode is P average is equal to 1 by 2 eta g TMMN mode. Same formula, student, but in place of eta g TMN, eta g for TM mode you have to write. Okay, eta g for TM mode. If you want, you can put this brackets here so that you will not be confused. This is all eta g only, but you have written eta g guide impedance for TMN mode. Okay, double integral electric field x component square, electric field y component square, and dx dy, x varying from 0 to a, y varying from 0 to b, that is equal to eta g for TMMN mode divided by 2 double integral, here the numerator means hx square plus hy square and dx dy, x varying from 0 to a, y varying from 0 to b, students, where eta g for TMMN mode is equal to eta into this factor comes in the numerator fcmn by f whole square, where eta is equal to root mu by epsilon, right. No need to remember these formulas, I told you, because these are general equations. Always we send the power in the T10 mode, dominant mode, and we will do derivation for that, right, students. So here also I will write one more observation and I will do the derivation. Final formula I will write in the note. For a greater than b in rectangular waveguide, T10 is a dominant mode. Okay. For T10 mode, field equations are already you have written, na, student. Hz is equal to h0z, that means initial value. H means magnetic field, naught means initial value of z component, that is the meaning of that. Then cos m pi by a into x, m is 1, so cos m pi by a x, then cos n pi by n is 0, so you get this one, e power minus j beta g into z. Next, electric field x component has E0x into cos and sine was there. If you put n0, then this becomes 0. Already we have studied this while drawing the what do you say, while drawing the the field configurations, shape of the field. Okay, then I told you, if electric field x component is 0, automatically magnetic field y component becomes 0. Next, electric field y component is equal to E0y. E0y means initial electric field for y component. Then it was actually sine and cos was there. Sine and cos was there. So then got sine pi by ax. Actually, sine m pi by ax for 1 0 mode m is equal to 1, and cos n pi by b into y, n 0, cos 0 is 1 actually. So e power minus of j beta z. Already I have written, you can turn the pages and you can see. So if this is there, actually this generates magnetic field x component, that is H0x, then sine pi by a x e power minus j beta gz. Now if this is 0, that 0 component generates what do you say, magnetic field y component is 0. Now dear students, you see here, in the T10 mode, electric field y component is there. The magnitude of electric field y component is E0y, and electric field y component is there. That electric field y component magnitude is E0y, and the magnetic field as x component, the magnitude is H0x. That means average power should be in terms of E0y, or otherwise you want to represent in terms of magnetic field, then it should be like H0x. Okay. Now here, total electric field modulus of Ex square plus modulus of Ey square is equal to modulus of this is 0 plus what is the modulus of this, student? If you take mod of this e power j theta, mod is root of cos square theta plus sin square theta, that is 1, then only this remains, that is E0y square, and then sin square pi by ax. Okay, right students? Then sin square theta is nothing but this is E0y square. This is 1 minus cos 2 theta, so that is by 2. This one, sin square is 1 minus cos 2 theta by 2. So here pi by a x is theta, 2 into that one you get. Now average power carried by rectangular waveguide, that story I will write in the note, student. Average power carried I will write, okay, is equal to, because no, this is observation is going on, then I will put in the box, no, there I will write everything neatly. So average power carried is equal to, so PAVG. Dear students, the formula used is this one. This is TE mode we are talking of. For TE mode we are talking of electric fields, and this one. So 1 by 2 eta g TE 10 mode, that is, then this one dx dy. So 1 divided by 2 eta g TE10 mode and double integral electric field. If you want directly, okay, if you want I will write the formula dx dy. Then this is the original formula. You substitute eta g TE10, actually, okay, eta g TE10 double integral. Here Ex is 0. This already I have done this one. That is E0 y square. Then 1 minus of cos 2 pi by ax divided by 2 dx dy. So ultimately, students, here 2 is there already in the formula. 2 is there means here you are going to use maximum values. This is not RMS value, this is maximum value. Like this student, in the network theory, average power is equal to half into Vm into Im into cos theta. These are maximum values. Whenever you remember in powers, half is there maximum values. Half is not there means they are Vrms into Irms into cos theta, students. Okay, like that. So here half is there already in the formula. Here sine square becomes 1 minus cos 2 theta by 2. From this again half came. So total 1 by 4 came here. Next, eta g TE10 mode. Then E naught square E0y square came out. Then integral this one 1 by 1 only is 1 by 2 pulled out. Integral 1 dx minus integral cos 2 pi by ax dx x from 0 to a and x from 0 to a. This is x term and there are no y terms. Integral dy y from 0 to b. Actually, this is all x term only. So you take integral dx here and integral dx for this also half came out. Now this is actually 0. This is actually integral dx is x. So this one you get integral dx is x. X from 0 to a minus 0. This is similarly this one. Because the integration of cos signal over a period is 0. You do that, you get 0 only. And this is y 0 to b. And this one is E0 y square divided by 4 eta g TE10 mod. This is A, this is B. A into B is area of the input end of the waveguide. Area of the input end of the waveguide. So if this is the waveguide, then A is this one, B is this one, this is the open end, then area of that is A into B. So after doing a derivation, dear students, I am writing the formula what to remember in entire discussion. Only you have to remember the formula what I am writing here, students. In rectangular waveguide, if A greater than B, then T10 is dominant mode. The average power carried by rectangular waveguide in T10 mode is PAVG is equal to E0y square divided by 4 eta g for TE10 mode multiplied with A into B area watts. That is equal to E electric field Y component is there, or otherwise magnetic field X component is there. If you write magnetic field component is given in examination, that is H0X is given square, then this impedance will be beside this. So then you get eta g T10 mode divided by 4 A into B watts, right? Now this is the formula, and where eta g TE10 mode is equal to eta divided by root of 1 minus FC10 divided by F whole square, where that eta is equal to root mu by epsilon. This thing you have to put in the box, student. This thing you have to remember. Okay, so this is the formula. In examination, TE10 mode is given. Definitely that fellow gives E0Y value, and if electric field is not given, then magnetic field is given. If magnetic field is given, then this impedance will be in the numerator. Okay, then waveguide impedance for TE10 mode is eta by root of 1 minus FC10 by F whole square, and already you know FC10 is V by 2A, and eta is root mu by epsilon. And I want to write something, I will write here. Okay, otherwise I will write there. What I want to write is E0Y is called maximum value of the electric field Y component. Electric field is also called as dielectric stress, because electric field unit is volt per meter. If you apply electric field to the dielectric material, for example, if you apply 10 volt per meter electric field, then per each meter length, 10 volts electric field will be pulling the electrons in the dielectric. They apply the stress on that, on the dielectric material electrons. That is why it is called dielectric stress. So this is the maximum value, that is called maximum dielectric stress. What they can ask like this, in the rectangular waveguide, what is the maximum power which can be handled by the rectangular waveguide for maximum dielectric stress is 10 volt per meter. Name is looking little different for you. Maximum dielectric stress 10 volt per meter. Whose unit is volt per meter? That is electric field unit. That means 10 volt per meter you substitute here. 10 volt per meter whole square you substitute, then multiply with A into B. Then how much maximum power can be carried by the rectangular waveguide you get. If you send more than that, then rectangular waveguide may be heated up. Then it may destroy its characteristics. So anyway, I will write the continuation there, where eta is equal to root mu by epsilon for dielectric field waveguide. If it is air field waveguide, root mu naught by epsilon naught. So where continuation student, eta is equal to root mu by epsilon. Of course it is dielectric field. If it is air field, then mu naught by epsilon naught 125 you have to take. Now E0 Y is a maximum value of electric field Y component. E0Y is also called as a maximum dielectric stress. Of course, volt per meter is the unit, that is maximum dielectric stress. And A and B are dimensions, you know that. So this one you have to remember, students. Okay, students. Now we have studied a rectangular waveguide. In the rectangular waveguide, if A not equal to 0, then B tends to infinity. Then you get two infinite area conductor surfaces parallel to each other you get. So I will write that one. In the rectangular waveguide, if we put A not equal to 0 and B tends to infinity, then we get two infinite area parallel conductor walls. then we get two infinite area parallel conductor walls. It is called as parallel plane. Plane means surface. Parallel plane waveguide. So what I was telling you is that this is a waveguide. Here this is A and this is B. Okay, this is A, this is B. Now what I am telling you is A is not 0 means that is finite. B infinity means the height of this is infinite. That is the meaning. That means now you get actually there are two surfaces like this. There are two conductor surfaces which are like this. This is one conductor surface, this one, and this is another conductor surface like this. B infinity means this is z axis, y axis you are taking anyway height. Anyway, this is of infinity height, student. B is equal to this one. This is of infinity height. Then if this is of infinity height, the situation is like this. I will show you by taking two papers. The situation is like this. So this is one wall and this is another wall, and these walls are like this. So we were taking this as a x-axis. We were taking this as a x-axis. Then in x direction, A is width is finite. Okay. Then B is infinity. B infinity means this is the height of this conductor is up to infinity. This is also bottom side also infinity. This is infinite area conductor plate, this one. Now this here one more plate is there. Now the distance between the plates is here in this direction, that is A, small a units. Okay. Now it is not at all practical. It is theoretical discussion, because if anything dimension is infinity, then you can understand it is not practical. Now in this how EM wave travels, for example, anyway I am holding like this. If any EM wave hits this boundary, it hits like this. Again after hitting it comes, then here this surface will be there. Again it will be reflected. Then it will enter here and it will leave there. So that is called parallel plane waveguide. Okay. Now it is also called simply parallel waveguide. For that, what formulas come you see, and of course this is called what? This is called what? This one center line is called as waveguide axis. Waveguide axis. This is called axis. Now if EM wave enters like this at some angle called theta, and then again it will be coming like this, it is hitting like this, it will be going like this. Okay. Now this is called wave angle. Okay. Now let us discuss formulas one by one. FC Mn is equal to V by 2 root of M by A whole square N by B whole square. Okay. This is for rectangular waveguide. For rectangular waveguide. Now for parallel plane waveguide, A not equal to 0, B tends to infinity, then you get FC Mn is equal to V by 2, and here M by A whole square plus N by B. So here B is infinity. That means V by 2 M by A square plus N into 1 by 0, 1 by infinity is 0 square. Why I am doing like this? I wanted to tell you 1 by infinity is beside n integer. So 1 by infinity becomes 0. Now n into 0 is 0. You should understand this term is becoming 0 not because of n. This is becoming 0 because of 1 by b, that is b is infinity. Because of b dimension, this n is becoming 0, but actually n is not 0. Because of b value, this is becoming 0, dear students. So now that means here n is not there in this. So that is written as FCM. FCM, single integer is remaining now. So this is simply ultimately FCM, because n has gone, n multiplied with 0 here. FCM is equal to V, it is 0, then m by a square under root means m by a. So V times m by 2a you get. So this is the cutoff frequency for the parallel plane waveguide. So it is not at all important in exam mode, but rarely in IES exam, they will ask this one. Anyway, have a knowledge of parallel plane waveguide because you have studied rectangular waveguide. Simply it is extension of that one word is there. So having this knowledge is you get good feeling. So here FCM is called cutoff frequency of mth mode. Cutoff frequency of mth mode of parallel plane waveguide. Okay. Next, m is equal to 0, 1, 2 dash dash integer. That is nothing but number of half wave lengths of E bar field and H bar field of E comma H fields in x direction. In x direction. Next, where V is equal to 1 by root mu epsilon, that is C by root mu or epsilon r, if it is dielectric field. If it is air field, then V becomes C. That means V becomes C if it is air field. Next, A is distance. A is distance between parallel plates. Okay. Next, FCM, you know, cutoff frequency for mth mode of parallel waveguide. Next, already we have seen for rectangular waveguide, sin theta mn is equal to FCMN by F. This is for rectangular waveguide. Now, for parallel plane waveguide, sin theta m is equal to simply FCM by F. Already you know here what is FCM. This is written here, FCM. Then sin theta n, this is. So this is the formula. Now here theta m is wave angle for mth mode. Wave angle for mth mode, it is called. Of course, in parallel plane waveguide. Already I was telling you, na, this theta here, this one, this is waveguide axis. This theta is called wave angle. So that one. M is equal to 1 means first mode. M is equal to 2 means second mode, like that. Okay. So this is all about the parallel plane waveguide. This is more than enough. Now let us talk of rectangular cavity, or otherwise rectangular waveguide resonator. I told you in network theory, LC resonant circuit you study that resonates at resonant frequency, FR resonant frequency. Okay. Similarly, here also you have resonant circuit. In the network theory, LC components are available in such a way that resonant frequency is in hundreds of kilohertz. Now, that LC resonant circuit in the network theory that works for hundreds of kilohertz, but that won't work for gigahertz frequencies. For gigahertz frequencies, LC value should be very small, so that is not possible to design. That is why already in the rectangular waveguide you have seen the cutoff frequencies are in the range of gigahertz. So that is why using rectangular waveguide, rectangular cavity is manufactured, and that stores energy, because inside the rectangular waveguide, for example, if you take a rectangular waveguide, now inside that medium is there. That medium has parameters called epsilon and mu, and this epsilon stores energy, then that is called electric field. Mu also stores energy, that is called magnetic field. So inside the waveguide, if air is there, air has epsilon naught mu naught. Inside the waveguide, if dielectric is there, dielectric has epsilon mu values. Then in that medium that has volume, the volume of that medium is equal to volume of the rectangular cavity. A rectangular cavity means in the front end also closed with conductor wall, back end also closed with conductor wall. That means 6 conductor surfaces are there, like your room. आपके कमरा जैसा है वैसा ही है, वो 6 walls को conductor surface से manufacture किया हुआ है. Because for example, I am seeing this room here. Here air medium is there, in this epsilon mu is there, and now if EM energy is there, that EM energy hits this conductor wall, then it is reflected, again hits the top wall, it is reflected, so that it cannot go outside, it is confined. Confined means it is inside the rectangular cavity only. So my dear students, rectangular cavity means you take 2 more conductor walls and close the opening walls of the rectangular waveguide, so that becomes a rectangular cavity. That is called waveguide resonator, or otherwise rectangular cavity. It is used to store electromagnetic energy in gigahertz frequency range. So it stores energy at resonant frequency. The resonant frequency of the rectangular waveguide cavity is cutoff frequency of the rectangular waveguide cavity. Okay. So here na students, rectangular waveguide resonator, or simply it is called as a rectangular cavity. Cavity means inside hollow. That means inside that 6 conductor walls you have air medium, or otherwise dielectric medium. So rectangular waveguide resonator, or otherwise rectangular cavity. Okay. Now the diagram is, I am drawing here diagram. So this is x direction we were taking, and this is y direction, and of course this is z direction. This one is z direction we were taking. हम लोग ऐसा ले रहे थे, ये z direction है क्योंकि origin इधर है, x axis, y axis, z axis ऐसा. Rectangular waveguide means this side conductor wall, that is this side conductor wall, bottom and top conductor walls are there. Now this is called let us say this is a D, this is a D, and this is A, and this height is B, like this. Now if we put in rectangular waveguide, this is open, this is open. Now if we put one conductor wall here, this one, okay, this is a z is equal to 0 conductor wall, and this one student touching from here to here. Okay, this is actually this one I am writing, z is equal to d conductor wall. So two more conductor walls are there. Ultimately already you had a conductor walls here, x is equal to 0 conductor wall and x is equal to a conductor wall, and x is equal to 0 conductor wall. This one is called y is equal to 0 conductor wall, and this one is y is equal to b conductor wall. So ultimately total 6 conductor walls are there, and inside this dielectric is there. So the dielectric has epsilon mu, energy is stored. Actually signal is sent here, top side na here. If you want you can see the diagram here. So this one is rectangular waveguide. Dear students, you close this wall with conductor, that becomes cavity. Now this side also it is closed, so inside air medium is there. If then it is called air filled rectangular cavity. If dielectric is there, that is called dielectric filled rectangular cavity. Now from here na, or otherwise from this side, here hole is drilled. After drilling the hole, exactly pen like structure is inserted. This is called coaxial cable. This coaxial cable has here like this coaxial cable, it has inner conductor and outer conductor. This coaxial cable has inner conductor and outer conductor. Now this inner conductor tip is taken, this is coax. Coax means coaxial cable. Short name of coaxial cable is coax. This one inner conductor is there, that is called probe. Now if you insert that into the waveguide like this, it is inserted here. From this side it is inserted, it is visible here. From this probe it will radiate energy into the waveguide cavity. Then inside this epsilon is there, mu is there, and they store that energy in the form of electric and magnetic field. That is the way energy is stored, dear student. So here hole is drilled, in that hole this coaxial cable is inserted. Then if you insert that it will be looking like this. So here this tip is there, that is called conductor probe, PROBE, probe. then that radiates energy into this cavity, then energy is stored here. Okay, dear students. Right. Now I am writing here if we place, मतलब if we place मतलब रखना है, if we place two more conductor walls at the open ends of the rectangular waveguide, then it becomes a rectangular cavity of volume A multiplied with B multiplied with D. Okay, this much volume, meter cube. Of course, it is generally in centimeter cube, but you can convert centimeters to meters, that already you know, student. In general, here A greater than B less than D होता है, और dimensions ऐसा होता है A greater than B less than D. Actually, the length of this is more. If length of this is more, then volume is more. It can hold more volume of, if more volume is there, it can store more energy. Right, students? This is the dimension actually. Already for rectangular waveguide A greater than B, but this D new dimension, that is much bigger actually. Okay. So, this rectangular cavity is used to store electromagnetic energy at resonant frequency, that is cutoff frequency of rectangular cavity. EM, electromagnetic EM means EM energy is stored in the dielectric medium present between conductor walls. Right? That means epsilon is there, then electric energy is stored, mu is there, magnetic energy is stored. Now once again it has two modes, TE mode and TM mode. So in this TE mode, it has a TE mode MN. Actually, student, in x direction you have seen, na, till now I was telling you, parallel plane waveguide, na, parallel plane waveguide, A not 0, only one integer is there. Rectangular waveguide, A not 0, B not 0. That means in A direction also it is bounded. Here only in x direction it is bounded. One integer you got. Here in both directions, in x direction and y direction bounded. So FCMN you get. Two integers you get. In rectangular cavity, A not equal to 0, B not equal to 0, D not equal to 0, you get FCMNP. Three integers you get. In three directions integers you get. So that is the discussion, right? Then here actually B infinity. So if you substitute in rectangular waveguide A infinity, B infinity, of course D infinity, then that becomes uniform plane wave. Uniform plane wave. They are all interlinked actually. Anyway, let us not go into the details. So TEMNP mode for wave traveling in Z direction, for wave traveling in Z direction, by definition of T mode, EZS 0 and HZS not 0, this is the main component. Okay, that means you write the equation of HZ. Students, here some students will confuse, sir, rectangular cavity means EM wave is not traveled, EM wave is stopped. No, some students will ask, EM wave will stop, they will ask. But you should understand, this cavity is used to store the EM energy. Here you will be inserting one probe like this. Here you will be insert one probe like this, coaxial cable. That coaxial cable sends energy into this, like this probe is there, inner conductor, that is coaxial cable. So when you want to store the energy, first of all you have to send the energy. At the beginning, if you send the energy that travels in Z direction, once if energy is filled up, then it stops receiving the energy, that one. So at the beginning, EM wave travels in longer dimension, the D is bigger actually here. A greater than B, D is bigger than A and B here. Okay, so that is the discussion. Now here HZS is equal to H0Z initial value. For rectangular waveguide for TMN mode, it was cos m pi by A x cos n pi by B into y. Ultimately, third term you get sin p pi by D into Z you get, because there is no wave propagation. Here P is also integer, D is length of the waveguide in Z direction. So here, dear students, P is equal to, you cannot put 0 here. If you put 0, no, P 0, P is integer actually. If you put 0, this becomes 0, then no component, no fields at all. So P value is permitted only 1, 2, 3, dash, dash, dash. So this is integer. The physical meaning is number of half wave lengths, number of half wavelengths of E comma H fields in Z direction, because 0 is not permitted here. Now FCMNP cutoff frequency for MNP mode is the formula is like this, students. Already you have seen at the beginning, 1 by 2 pi root mu epsilon root of m pi by A whole square plus n pi by B whole square plus P integer by D whole square. This is the formula. And pi square comes out now, pi cancel, then m by A whole square plus n by B whole square plus P by D whole square. This FCMNP is called cutoff frequency for MNP mode. The same cutoff frequency valid for TMMNP mode also. And this itself is called as a resonant frequency. It stores energy at this resonant frequency. Right, students? Now, here, dominant mode later on I will write, okay? Dominant mode cutoff frequency, no? Then let us talk of TMMNP mode. Once again, for wave traveling in Z direction, by definition of TM mode EZS not 0, HZS is equal to 0. Here EZS for this mode is electric field initial value, then sine m pi by A. Once again you get sine n pi by by. Then here you get cos p pi by dz. Now here p can be 0 also, no problem. P varying from 0, 1, 2, 3 dash dash integer. The meaning is same. Number of half wavelengths of electric and magnetic field in z direction, that is. We are not writing Mn, already Mn written earlier, so the same meaning here. Once again here also Fc Mnp is equal to 1 by 2 pi root mu epsilon and root of m pi by A whole square, same formula, n pi by b whole square plus p pi by d, p multiplied with pi by d whole square. So here students, this is A. If it is the air field, then mu naught epsilon naught you have to take. Okay. So anyway, if they ask objective question, then in TMNP mode, magnetic field is cos sine. This is sine cos. You remember, because cos it cannot become 0. So even P0 P0, then cos 0 is 1. It won't make that component 0. Here P is equal to 0 is permitted, 0 value, but here P 0 value not permitted. Now one objective question is there. What is the dominant mode in the rectangular cavity? So here students, already TE10 is the dominant mode in rectangular waveguide for A greater than B. What is the concept of dominant mode? So this is the cutoff frequency formula. For example, A greater than B, then A is bigger, B is smaller. In the denominator, bigger value is taken, then in numerator smaller value, then cutoff frequency becomes smaller value. Dominant mode means least cutoff frequency. So in this way, if A is bigger, B is smaller, then B is smaller, you put this integer 0, then smaller value in the denominator is eliminated, so that you put m is equal to 1, then A, that is bigger value in the denominator, is remaining. If bigger value is there in the denominator, in the numerator smaller value you get, that is the dominant mode, lowest cutoff frequency you get. So if A greater than B, this is the dominant mode. Then for the cavity, A greater than B less than D, then TE101 mode is the dominant mode. The reason you know now, this is the smaller value among them. You don't take small value in the denominator. For that n0 you substitute, then you are putting 1, that means A and D are present. A is present in the denominator, bigger value, that is D is also present in the denominator, that is bigger value. In the denominator bigger values are there, then in numerator smallest value you get, then Fc will be least, that is called dominant mode. That is called dominant mode. So dear student, this is the extension of this one. Already it is decided if A greater than B, least cutoff frequency for 1, 0. Then D also came. D is a bigger value compared to them. So you take that bigger value in the denominator, you get least value in the numerator. So that is the way you remember. A note I am writing here. For rectangular cavity TE101 has least cutoff frequency for A greater than B less than D. So TE101 is the dominant mode, right? So this is also objective question, important objective question. You have to remember that one, right, students? Now we will talk of circular waveguide, students. Okay, that circular waveguide discussion will be exactly similar to this cutoff frequency formulas and all. We have to see. We will discuss that. So, dear students, before discussing circular waveguides, now let us talk of one more note. In rectangular waveguide, for A greater than B, the dominant mode is TE10 mode having FC10 cutoff frequency. FC10 cutoff frequency. If you take next higher order mode, next higher frequency mode, higher order means next higher frequency mode. Then if you send EM energy between FC10 and next higher order cutoff frequency, up to next higher order cutoff frequency, then it behaves like a band pass filter. Band pass filter. Right. Now, there are two cases. Case 1. Case 1. If A greater than B and A greater than 2B, then TE10 mode has least TE10 mode has least cutoff frequency and next higher cutoff frequency is for TE20 mode. You will ask me questions, or what is going on? A greater than 2B, A greater than B, what is the meaning of this? Don't worry. I will explain this while solving one workbook question. There two cases are there. You have to remember the modes in increasing order of their cutoff frequencies. If A greater than B and A greater than 2B, one case. Another case is if A greater than B and A less than 2B, that is another case. We will discuss there. So, if A greater than B and A greater than 2B, then TE10 mode has least cutoff frequency. Then next higher cutoff frequency is for TE20 mode. That means FC10 is cutoff frequency for TE10 mode. Okay, so FC20 is cutoff frequency for TE20 mode. Then if operating frequency F is in the range FC10 less than F less than FC20, then rectangular waveguide behaves like a band pass filter which can send frequencies between FC10 and FC20. So just a band pass filter means that can send frequencies in between, right? Like this. If you take gain, then this is frequency. Now this is FC10, this is FC20. Here gain is maintained 1 for transmission structure. This is band pass filter. So bandwidth is equal to FC20 minus FC10, bandwidth of this. Okay, students, already you know no cutoff frequency FCMN formula. From that only you get this one. So that is FCMN is equal to V by 2 root M by A whole square N by B whole square. Next, case 2. If A greater than B and A less than 2B, right, dear students? I will solve them, don't worry. In the workbook, one question is there. If A greater than B and A less than 2B, then T10 mode has least cutoff frequency, comma, and next higher cutoff frequency, is for TE01 mode. So if for this case, if you calculate the cutoff frequencies, least cutoff frequency comes for TE10, that is FC10 frequency. Then next higher cutoff frequency is FC01, that is for TE01 mode. Then again it behaves like a band pass filter carrying frequencies from FC10 to FC01. Okay, dear friends, right? Now FC, similar to that I am writing FC10 is cutoff frequency for T10 mode, and FC01 is cutoff frequency for TE01 mode, right? Next, if the operating frequency F is in the range FC10 less than F less than FC01, then rectangular waveguide behaves like a band pass filter for this frequency range. Okay, that means it is gain for transmission structure. Highest gain is 1. Already I told you. Gain 1 means input signal strength is equal to output signal strength. So losses in that is 0. That is the meaning. F here. Now this is FC10. So here FC01 like this. This is gain 1. Now bandwidth is equal to FC01 minus FC10. So this is the bandwidth, student, right?